As I said to you guys before, this is a session that is much in demand. We have specially provided a link to people dialing in from outside. So we have many invisible guests dialing into this one, lots of healthcare companies, because this is a healthcare story. And of course, healthcare data and pets is a great use case and a great example of how pets can be used. Rena has collaborators dialing in as well. So bear with us as we mastermind this technically complex session. Rena, do you want to come over while I drag everyone else in from outside with their coffees? So bear with me as I bring more people in, but you can kick off.
Sure.
Here's your clicker.
So we will be focusing on actually use cases, and because this whole event is very much focusing on adoption of pets. As you know, the industry and academia have been talking, and also the legal regulators and people from the legal areas have been talking about how to combine privacy and technology for a while. So we are a few good years into this. And there are many questions like ROI and business value and the compliance, and it's all kind of, still the industry is making efforts to adapt, but we thought it would be very helpful to actually present two use cases. They both happen to be from healthcare, but the platform and the technology is really domain agnostic, and it can be used, the same technology, the same sets of pets that we will be talking about can be used also for other industries. And some of the things that were said earlier today really very well resonated with us as well. And like especially Julian was saying, there is some magic in these technologies, and the magic has to do with the fact that often they allow parties to collaborate without exposing what they want to protect. So it's not about preventing access to information, but actually extracting value from data, extracting information that is needed, but without exposing the sensitive parts of that information. And there is a lot of magic in that. And many of the pets are actually used for collaborative purposes. And when we say collaboration, it often has to do with, can be cross-departmental, can be cross-organizational, can be cross-border even, and can be between organization and the cloud. So it's anywhere the trust boundary exists. So without further ado, we will just jump into this, and we'll have also time for Q&A and summary at the end. So let's start. So this is the basically the agenda for today. And we have people participating. As Monisha said, two of my colleagues from Israel will be connecting, and our VP product, Adi Hirstein, and our senior data scientist, Oded Rosolio, and they are both involved with these use cases, supporting them. And also, we are really happy to have Associate Professor from Dana-Farber Cancer Institute, Alexander Gusiev, who has been actually using those technologies in his cancer institute. And he will be explaining, and I think it's very important, the motivation, why they need it, why he's using it, what he is achieving. And then we will explain how the platform supports it, how the pets support this use case. And then we have another use case that has to do with cross-border collaboration also in healthcare and actual demo. So we will be demonstrating also. So I know there are quite a few technical people. It will be a very short one, so not too complex. So we will now move to Dana-Farber, and hopefully Sasha is connected, and let's see that he can actually
can you
start.
Can
yes,
you hear me, Irina?
We can hear, and hopefully we can see you now. Okay.
It'll come up, yeah. Great. Well, thank you so much, and thanks everybody for attending. I'm very excited to present work that we've been doing in collaboration with Duality, using these privacy-preserving technologies in the clinical setting for understanding, diagnosing, and improving the treatment of cancers. Next slide. And the next slide. So I'm going to be focusing, I guess I'll be saying the word slide a lot because I'm going to be talking about digital pathology slide use case that we've been employing together with sensitive clinical data to improve cancer diagnosis for patients. So I'll motivate a bit why this is an interesting data type, and in particular why it's a useful data type for I think these techniques that we'll be describing specifically. I'll talk about some prior work that we have done and where we hit a wall in terms of collaboration needs that we weren't able to meet without this technology. And then I'll present some pilot results to kind of demonstrate to you that, that we're able to already get substantial gains by, in this case, using secure federated learning, and thoughts about where this kind of work can continue to go with this platform. So next slide, Rena. So the fundamental data type that I'm going to be discussing is a digital pathology slide. Sometimes you may see it referred to as an H&E slide or histopathology. I'll just talk about them as digital slides. The basic idea is that in the cancer setting, the way that tumors are diagnosed is a biopsy is taken from a patient. A slice of that biopsy is placed on a glass slide, and that slide is often digitized. And what you get looks something like the figure on the right, which is an extremely rich, detailed, high-dimensional spatial information about the tumor. And you can see in those little sort of call-out dots that, in fact, not only is there global spatial structure that is important to the diagnosis, like the sort of dark area, the outlined area represents the actual malignant tissue, but there's nearby healthy tissue that may be informative about the cancer progression. Additionally, within each of those call-outs, you see really, really detailed granularity about the image, including cellular level, like individual cells that can be observed, and potentially visual details about those individual cells, how mutated, how aggressive, how unusual they are. All of these kinds of features are captured in this slide, and this, together with other clinical factors about the patient, are actually how a diagnosis of what kind of cancer, whether you have a breast cancer that maybe has metastasized to the lung or a lung cancer that started in the lung, this data is the information that's used for that diagnosis. Next slide. And I guess the other thing that's worth mentioning is that this is, in some sense, the most routinely collected clinical data. And so it presents a real opportunity to apply machine learning techniques because it's high dimensional, it's extremely information rich, and there are probably tens of millions, if not more, slides like this that have been collected from cancer biopsies in routine settings because it's part of the standard diagnostic workup. And so there's been kind of an explosion in the field of applying machine learning techniques, typically convolutional neural nets or other deep learning frameworks, to learn information from these digital pathology slides. And this is just an example of one basic structure which attempts to, and this is pretty common, reduce the slide to individual features, but then aggregate information across all of those features and train on some kind of either classification task or multi-class prediction, or possibly even a survival or clinical outcome task. And this has worked already, even with sort of fairly standard and small scale data sets, has been remarkably successful. So next slide. Here's an example from a recent paper looking at the ability of a neural net algorithm applied to digital slides to classify cancer. So this is sort of reproducing the work that the human pathologist does. And you can see in the red line, which is like the most recent state-of-the-art method, cancer classification accuracy of with AUCs of above 0.9, sometimes even higher. Additionally, there are examples, I know it's a very detailed plot, but there are some examples here of subclassification of subtypes, which is a particularly difficult task, and even identification of certain precise mutational features, which basically requires identifying those individual cells and trying to extract factors from those individual cells. Next slide. This is still a work in progress, though. This approach hasn't solved, and the field hasn't solved every single problem. For example, it's very important to be able to classify whether a tumor is hypermutable versus not. And this kind of information can be gleaned from the image. A very skilled pathologist can spend a lot of time and evaluate to what extent a tumor appears to be hypermutable. And the algorithm, the computer is starting to catch up. You can see, AUCs here of about 0.8 or 0.85. But obviously, we're not yet at the level of human-based classification. And I suspect, and I think a lot of people in the field think this is primarily a data bottleneck. At the moment, most studies have been restricted to single institutions. Next slide. So that's to give you a bit of a background of the state of the art. That paper that I just mentioned came out a few months ago, so you're really caught up. And now I want to talk about the specific project that we've been engaging in this collaboration in using clinical data at Dana-Farber and at other nearby institutions. And what we are attempting to do is classify a group of cancers called cancer of unknown primary, which are specifically defined by the characteristic that the pathologist does not know, cannot tell directly from the slide what type of cancer it is. It's diagnosed as unknown, and then these patients have very, very limited treatment options as a consequence. Most treatments are specific to a given cancer. There's a very specific clinical path for breast cancers, for example, and if you don't know which kind of cancer you have, your options are highly limited. Next slide. So in the past, we have already demonstrated that this task can benefit from some machine learning. So we've developed an algorithm, you can see from the title here, that's genetics based. So we're using sequencing information from these tumors and making classifications based on the mutations that they have. And that kind of data has now been, because it only involves information about the tumor, has been made publicly available. And so we were able to leverage a large amount of training data from multiple institutions to apply to this task. Next slide. We used a fairly standard random forest classifier. We're putting in somatic information. We're classifying cancer label based on known cancers. Next slide. And we showed that this is a potentially solvable problem, that for a number of cancer types, the accuracy or F1 score of this classifier is quite high. But you can see that actually in a lot of instances, there's still work to be done. And I won't get into the details, but the cancers that this algorithm is struggling with are actually probably the ones most common in the unknown primary setting. So those are the most important ones to improve. Next slide. The other, I think, important point that we demonstrated in this prior work is that once you deploy this classification on unknown primaries, you do see differences in survival outcomes. So in principle, this approach can already be used to stratify whether an individual is high risk or low risk. So each curve here is showing a different predicted cancer population, and demonstrating that there are actually subsets of unknown primary individuals who do quite well, who have long-term survival, and others who do really poorly. And knowing that information alone would already be extremely useful. Next slide. And so coming back to this point of incorporating digital pathology or H&E data, we have started exploring the possibility of expanding this algorithm to go beyond genetics and to use these digital images. So we're training an ensemble model that includes both the somatic mutational data, now features from the digital slides pushed through a convolutional neural net. And we see that, in fact, not only do these two approaches tend to be fairly concordant, they are also able to identify to make predictions that the other approach has low confidence in. So this is sort of ideal for an ensemble, multimodal data setting where there's somewhat different but typically concordant information going into these models. Next slide. And so with that in mind, that kind of brings us to the challenge. It seems like we have something on our hands that could be very effective and push the state of the art forward for these cancer classifications. But the issue is that working with this digital slide data is much more challenging than working with the genetic data that we were using before, which you can just go and download on the web right now. These images are, first of all, very large. You can see the dimensionality of the data. One image can be made, many hundreds of gigabytes, and we want to train on tens of thousands, if not more, of such images. And institutions are just much, much more hesitant to share this kind of data. First of all, at a very basic level, the image often contains private patient or clinical information. Sometimes the patient's record number will be written on the corner of the slide, but sometimes it's more subtle clinical factors that really cannot be released and under legal penalty. And de-identifying this kind of data or guaranteeing that it can be released in a secure way is extremely difficult, and basically very, very few institutions have done it. The other point that I want to make is this is also a space where you need complex machine learning algorithms because of the dimensionality. There's not really a way to extract some secure summary level information about these slides. You kind of need to learn from a lot of different patches and sources of information and integrate it all together. And a sort of more subtle point, which I'll actually get to in some of our results, is that this kind of training really needs to be done across institutions because there are many institute-specific batch effects. The coloring, the contrast, the shape and size of these slides can all differ by institutions, and it's very common for these algorithms to overfit to a specific pattern that happens at one hospital and then to completely fall apart when they're shifted to another hospital, and that really cannot work. And so we've been partnering with Duality to deploy federated learning approaches to address all of these problems, and I think these are problems that are true of other complex large-scale clinical data. Next slide. So the specific framework I'll just gloss over because there's going to be more about this later in the talk, but we're using a federated approach where there are 3 different medical centers. We're working with Mass General Hospital on this, and we're also using a third public data set. Those individual centers are storing their data securely. They are training components of the model within each of those nodes, and then they're securely sharing the weights during the training process, a model aggregation node that then combines those weights, returns back the sort of subsequent iterative step to the algorithm to each of the nodes, and this process operates iteratively until convergence. Next slide. So we wanted to first demonstrate that this approach is actually feasible, that the nodes don't just collapse, or that data is able to stay secure. And so, as I mentioned, we've been working across 3 institutions, one of which is public data. We've been deploying this on the Google Cloud platform together with the Duality Federated Learning Framework, so that data is stored securely at each at a node that belongs to each individual institution. And we started off by just tackling one of these subtype classification tasks. We want to distinguish between two types of lung cancer, for example, which is actually a sort of medium hard problem. Like the state of the art is not perfect there yet. Next slide. So I'll kind of rush through the results because I don't want to get too much into the weeds here, but the basic point is that when we combine information across multiple nodes, we do indeed see a significant increase in accuracy here. So you can see as a function of training size, either 50 samples in each node or 100 samples in each node, we consistently see superior performance by working with more data across institutions than within one institution. And in fact, those sort of white bars on the left are basically not actionable, like the performance is too poor to be used, but the blue bars are starting to get to a point where they could actually be incorporated. Next slide. Additionally, we see that this approach is actually more efficient than processing the data kind of one node at a time in total. So on the left, you can see two institutions with fairly balanced data sets. The federated approach converges faster and takes less runtime than the two institutions on their own. On the right, you can see a kind of imbalanced scenario where one institution has massive slides and the other has much smaller slides. And here, actually, the federated approach is more efficient than the massive data set. So if you have a lot of data, you can actually benefit from improved learning across other institutions that have smaller amounts of data. Next slide. And then finally, because I'm a researcher, I also want to make, I think, an interesting research finding that we've observed, which is that the performance of these models across the different institutions can vary a lot. And it can also change your interpretation of how to pre-train the data. So on the left, we're actually using a foundation model to do the initial feature extraction. And you can see that sometimes the foundation model performs beautifully and sometimes it's quite poor. On the right, we're using a more standard ResNet approach. And you can see that the accuracy is more balanced across the institutions. This is information that we couldn't have gotten without a federated approach. So separate from the benefits of improved accuracy and efficiency is just the point that from a research perspective, this problem is much more informed by working across many institutions. Next slide. And so with that, I think I'll skip the summary and maybe the next slide. Oh, yeah. So I guess the last thing that I wanted to mention, maybe wasn't in that summary slide, is just that not only are we able to do this now within the Duality framework, but we've, as part of this collaboration, we've also started working on extensions to these methodologies. The Duality platform allows us to use custom loss functions, for example, to do direct survival prediction, to change the network architecture, and to change the type of evaluations that we're doing. So this is really just a pilot, and we're sort of continuing to develop this together. And thank you.
Thank you, Sasha. So we will continue, and I just wanted to make a point that connects to the previous panel, that you see the domain is the requirement and the need comes from the domain. The domain is very complex by itself. So if we were just to come to Dana-Farber and say, here, pets, wonderful pets, why wouldn't you use them? They wouldn't know how to connect it necessarily to the problems they are trying to solve. The need comes from the domain, the fact that they need more data. By the way, that can be definitely generalized because many use cases simply require more data in order to get better results. And that's when the pets come as a solution. So they don't have ROI on their own very often. They might have, one can build the economic use case for sure, but they definitely help overcoming barriers that otherwise this kind of projects probably wouldn't happen. And this is very important because it allows cancer research can have crime research, can fraud research, or identifying fraud. So there are many, many use cases, but the driver comes from the domain, and domain is pretty complex by itself. So now we will accelerate a little bit, and Adi will say a few words how this actually being achieved by the platform, like how the pets play here, and we'll continue then. Okay, Adi, please.
Yeah, thanks, Rina. Hi, everyone. Happy to virtually participate in this webinar. I'm going to talk about not just PET, but how we can actually facilitate those type of collaboration. If you move to the next slide, please. And from our experience, basically share what are the type of elements that you actually need for real-world collaboration projects, and PET is definitely one of them, but it's not the only thing. And when you typically build a collaboration project, there are a couple of aspects. The first one is kind of basic, the collaboration itself. How do you facilitate those collaboration in terms of the right architecture? Who is managing the collaboration? How do you invite people, manage the roles of the various participants, and so on and so forth? The second piece is the workload itself. What kind of workloads are you going to run? Is it going to be like a decentralized workload, like federated learning, like the example that Sasha mentioned, or is it like more centralized approach that has impact on the way we build the architecture? And in general, whether it's training of a model or inference or statistical analytics or even queries, that has impact on the way that we facilitate those collaboration projects. And the third piece is obviously the privacy preserving technologies. So there are a bunch of technologies that we have. We'll talk about them in a second, all the way from FHE to TEE, federated learning, and even more. And you need to choose the right technologies. And in some cases, there is a combination of multiple technologies altogether for those specific projects, like in the case of Dana-Farber. So moving on to the next slide. So we built a platform that basically addresses all those challenges. And the platform comprises of three parts. So the first part is what the first layer is collaboration management layer. Those are all the features and the capabilities that you need in order to facilitate those collaboration, all the way, again, from the basic stuff of inviting participants and managing their roles and things along those lines, and even determining who is the collaboration admin and what is the role of the admin is things on his own, all the way through the data management. So think about it, if you have multiple data sets across different organizations, how do you make sure that everything is aligned? How do you run, let's say, processing on the data so you can actually run federated learning or federated analytics? So in many cases, you need to run some pre-processing, or if it's a structured data, you may need to align schemas. So simplifying that piece and doing the harmonization is obviously an important element. And then there is the governance and control. As a data owner, I want to make sure that they know exactly who is accessing my data, at what frequency, what kind of workloads they are running, and even more than that, I'd like to set up some specific rules. Like, for instance, if somebody is asking a specific question and the result is below a certain threshold, I want to be able to block that. So there are many aspects that goes under governance. The other piece is exploration. If you build a new model, as a data scientist, you know that you can't really start from scratch. You need to see something. That could be the schema or sample data, but you need to be able to get some information in order to start running or building your model. So we are helping also with the exploration phase. And the other part here, as an admin, I need to be able to monitor everything that is going on and to get the auditing for the system and so forth and so forth. And in general, we're providing a user interface, but in addition to the user interface, we also provide APIs and SDK. So for the most part, data scientists are using SDK. We have partners that are using APIs in order to build applications on top of it. So that's kind of the first layer. The second layer is the computation layer, and this is where you can run basically any kind of computation. So it can be machine learning, training of a model, or inference. It could be statistical computation, even queries, or arbitrary computation. And then once you create or start a workload, it also has impact on the type of privacy-enhancing technology that we're going to choose. So the third layer is those privacy-enhancing technologies, and we've started as a company with a very advanced encryption methodology or encryption architecture called homomorphic encryption, fully homomorphic encryption. In very high level, it provides the ability to take data, encrypt the data, and run operation on the data while the data is encrypted without decrypting it. So it's very strong security, encrypting security. It basically post-quantum, and it serves for specific use cases. Then, in addition to FHE, we also have federated learning. So, as Sasha mentioned, in the case of Dana-Farber, we've been using federated learning, and the concept of federated learning means that the training happens at the edge. So, for the most part, the heavy lifting of the resources happens at the edge, and then only the intermediate weights or intermediate results are being sent to some sort of a central aggregator in order to create a global model. So that's the federated learning approach. And then the third privacy-enhancing technologies that we support is trusted execution environment. And specifically here, we're working with Google Confidential Space. For those who are not familiar with Confidential Space, it basically provides you a server with an isolated environment, so you can send encrypted data into that isolated box, and all the processing happens inside this isolated box without any ability to access the data. So not even Google can access what's going on there. So that's kind of the platform that we have, and the concept of our platform is basically under the assumption that there's no one-size-fits-all. And in many cases, you may need to combine different privacy-enhancing technologies. Like in the case of Dana-Farber, it's federated learning and confidential space. And we can see all other cases. So Dave is going to talk about some other use cases where we are actually incorporating additional privacy-enhancing technologies altogether. Next slide, please. So that was the platform. In terms of the benefits, if we think about what are the core benefits from our perspective by using the platform. So first and foremost, in many cases of research labs projects, it's a one-off project. And you can't really leverage the same assets and resources again and again. When you use a platform, you have the ability to do a repeatable research, and you can leverage it for other projects with different data, with different models. So obviously, it's completely repeatable. And the other part that we're putting lots of focus is the ease of use and how easy it's to onboard different users. And when I say different users, it could be a data scientist, by the way. But it could be also an analyst that just want to run some statistical computation. They don't need to develop anything, but they still need to get a very smooth experience in order to do that. So the platform puts lots of focus on those type of things to quickly onboard different types of personas. And then there is the aspects of development. So for instance, in the case of federated learning, if you want to take a model, in the case of Dana-Farber, they've been using a model called CLAM, and convert it, if you will, to a distributed model that requires some work, some development work. Oded, that is going to talk later on, actually did that work. And we as a company, provides those support to take, and the engineering resources in order to take those models and convert them to a distributed model, to federated model, so that you can actually run them on the platform. And then in terms of the data, obviously we support any data, any model. That's extremely important to combine structured data and unstructured data all together. Cost effectiveness, specifically when you do federated learning, and I think Sasha also saw that in his case, particularly when the size of the data is large, like pathology images is almost like 1 gigabyte per image. And if you have tens of thousands of images, putting everything in a centralized place is going to be much more costly than running it in a federated approach. So the cost effectiveness is yet another thing to take under consideration. And last but not least, the privacy enhancing technologies and the fact that you can protect the data, you can protect the model, you can combine different technologies like federated learning and trusted execution environment and FHE and even others that we've added along the way, like differential privacies and the governance altogether are extremely, extremely important. So that's pretty much what I wanted to cover. I think that the bottom line here is that beyond the privacy enhancing technologies, the core technologies, there are lots of other stuff that you need to do in order to facilitate those collaboration projects. I just wanted to give you some taste of our experience in the real world with real projects around that.
Thanks, Adi. And as always, the important work of vendors is how to make this complex stuff easy. So, because when you hear it all, it sounds so complex, but at the end, we really want organizations, in a way, focus on their needs and to make it really as easy as possible to actually use those technologies. So, since we are in the context of this PET summit, we need to remember that PETs tend to be very complex. And there is no actually need for organizations to understand the complexity. They mainly need to understand how this can help them solve the problem. So I think, again, the driver should come from what problems we are trying to solve. And so there is another use case which actually deals with sorry, I think we might be not in the right presentation because there were changes to the presentation. I don't know if you have the most recent one.
Rina, you want me to share? I can share.
I don't know if you can.
Odette can share.
Can you share, Odette,
yeah, for sure.
Yeah, so let's go back. So this one focuses on rare diseases, actually. And rare diseases is the most, I would say, natural category of use cases where you have to collaborate because there is a need for a much larger cohort. Rare diseases means you don't have many cases in each country, but there are many countries, and if it was only possible to collaborate on this data. So here you have an added dimension of difficulty. Not only you're collaborating across organizations, but you're also collaborating across borders. And actually, many multinationals have this kind of challenges because sometimes even between their departments, they have the cross-border challenges if they need to collaborate even between different departments. So even though we talk again about healthcare here, but the concept is very important, pets often help to collaborate. They help to collaborate often between data owners and model owners or even clouds are seen as another party. And they really help to resolve these difficulties and barriers of collaboration. So Oded, can you please run us? Oded actually works, he's our senior data scientist. He works on this cross-border case, and what makes it interesting for this PETS summit is that here we use 3 PETs in one solution. We use federated learning, we use trusted execution environment, and we use differential privacy. So, and it's all needed in order to protect the data properly. Okay, please. Oded?
Yeah, right. I hope you guys can hear me well. So I'm going to present the DCT use case, which we implement and deploy a computation of secure collaborative analytics. The motivation behind it, as Rina mentioned, is that the goal here is to actually do analytics on rare cancer types, where it's quite challenging because of the fact that those cancers are quite rare, and it's challenging to reach statistical significance due to the small counts of each cancer among individual institutions. Furthermore, if I want to analyze many kinds of cancers, and each institute specializes in a specific field, then there's an additional need to collaborate with other institutions and to allow the study of effectively the entirety of the data. So we want to enable the collaboration of many data providers to conduct a joint analytics, and also allow multiple researchers who's not necessarily affiliated with those institutions, and to allow them to submit queries and get results. Now, the problem here is mentioned here in this PET summit, that we're talking about sensitive data and even sensitive results. So not only does the data itself is private, one can gain a lot of insights on the individual level data just by really applying some clever algorithms on the results. And also, of course, there's the regulatory aspects of it, that you can't send your own data to be evaluated elsewhere. So this is a very simplified flow diagram of the data in a collaborative analytics deployment. So let's say that we have 2 data providers labeled here as data provider 1 and data provider 2. Of course, there can be a lot more. I'm showing here just 2 for simplification, where each of them has their own databases. Those data providers actually compute some of the computation on their own premise, and they send the intermediate results to a centralized node that takes those results and aggregate them in a specific way in order to obtain the results of the total data. And then that result has been sent to the third-party researcher that initially sent the query, and we treat him as the initiator or the inquirer. And of course, it can be more than one. The problem with this type of flow is that there are many privacy leakage places in the diagram. So, for instance, one can listen on the channel between the data provider and the aggregator and obtain the intermediate results. The aggregator can collude with one of the data providers and deduct the data of the other one, and many more. And in order to allow for a secure collaboration, we need to add some privacy layer. Now, different privacy tools actually tackle specific privacy concern, meaning there's a privacy layer that treats the data or information breach, another one that tackles collusion, another one that tackles re-identification, and the other kind of security breaches. And in order to gain a full privacy, it comes from the use of a combination of those components. So in essence, larger privacy is achieved by making those privacy layers to work together. So the privacy layer that we provide, as mentioned previously by Adi, is essentially fivefold. The first one is the federated analytics deployments, which makes sure that raw data never leaves the data owner's premise. The second one is differential privacy, where through the addition of controlled noise, you change a bit of the result in a smart way, making the party that receives the result to not be able to re-identify specific individuals from the original data set. We also have the privacy rules, which essentially it has the small count threshold in order to restrict the ability of the inquirer to receive information on low counts, very low counts of groups, and also K anonymity by really limiting the amount of filtering that can be done by the inquirer. We also implement the Trusted Execution Environment, or TEE, which basically means that once the data owner has computed its own intermediate result, he encrypts it, sends it into the secure enclave. Inside the secure enclave, that intermediate result is decrypted, and aggregation is taking place, and then the final result is sent. And we also have the layer of governance, which basically means that the collaboration manager is the one that is in charge of which privacy settings to use, which parameters to use, and also how many queries each individual can run, and even limiting the parameters used in specific workloads. So all those layers are configurable in the project level, meaning I can have several projects and list them as high privacy or low privacy according to their to the individual that use it. All right. So I'm going to go now.
I just want to ask maybe to do very quickly the demo, so we have some time left for questions. And so, yeah.
Right. So here we can see the Duality platform in those 4 tabs above. So if we look at the collaboration manager or the orchestrator, you can see that there are 3 participants: data provider 1 that serve as an asset owner, data provider 2 that serves also as an asset owner and as the compute or aggregated node, and the researcher that initiates the computation and finally gets its results back. And I can decide whether or not to use a secure enclave, and whether or not to use the different privacy mechanism and which parameters to use them by. So here we're just doing the default settings, but of course I can change it as I see fit, and this will be incorporated in the computation. If you go to the asset owner, node, then I can look at their data. Sorry, my VPN is off. All right, so we see the data for demo for the two participants. And now if I go to the initiator, I can start a session. Let's call it Google Demo 1. The workload I'm going to choose is one of the 4 that I've chosen beforehand. So we have cross-tabulation, histogram, observed survival rate, and ASR. So let's choose the observed survival rate. I'm choosing the data according to my participants. So the second data provider here, I'm choosing its data. I can add another participant and use its data. And if I want, I can use filters. I'm not going to do it now. But here, I need to supply the column to be the time column for the survival analysis or the survival time. The time base I want to use is since I know in advance that the data is given in months and I want a yearly survival analysis, then I have to use this list. The event column would be vitality status at last contact, and event indicator, which means what is the data that I'm using is dead. So it's 0 in this case. And I can press on start session, see the window that summarizes the different parameters, and wait until the session is created and run. It will take roughly 30 seconds. This actually transferred data from various machines in AWS. It doesn't run locally. It actually runs on a real deployment, so it will take a bit of time. So I pre-made it before, so we can view the results, or we just wait a few more seconds. Right. So it completed, and you can look at session details and can see the event at certain times. And I also have the survival rate at that time and the appropriate confidence intervals. And this is just a preview. If I want to download it into a pandas data frame, I can do it.
Okay.
I can do it, and I can also download it into a CSV format.
Okay, so we don't have much time for Q&A, and just for the summary, one sentence. This is like real world meets pets. In a sense, you have a real use case, a real problem. There is a need to collaborate. You need to overcome barriers of privacy, confidentiality, cross-border, etc. And this is how pets can help to address those concerns, to achieve, in this case, healthcare-related use cases. And we have many others in national security, fraud, and also impact analysis, which is very relevant also for the advertising space, where you have certain activity happens in one area, but it impacts results in another space, and you want to cross-correlate the activity with the results. It happens in many situations where the information is sensitive. So please, any questions? I know it was a lot, and started from very deep cancer information, and now also you saw a demo. So please, if you have questions, so very happy to address. Yeah, please.
I'm just coming with the mic. Hang on. Sorry.
What common attack is a membership inference? So do you protect against membership inference in the model?
So can you repeat, Henry? I couldn't hear.
Yes, yes. So in FL, in federated learning, the most common attack is membership inference. So do you protect also in your platform against membership inference attacks? And the
Most common attack is, sorry?
membership inference, meaning that by attacking the FL itself, you can try to figure out if somebody was in the model or not. So is this part of your protection methods? And then the second would be that, what about SMPC? So because multi-party computation might also be, for these multiple parties, interesting complement to FL. So FL with SMPC.
Mm-hmm. So, Odette, can you address the question about, have you heard the question about attacking?
Yeah, we heard it. I think what I understood from
Sorry,
the question
we
is that,
can't hear you.
attack. You can hear me?
Yeah.
Okay. So attacks from the communication of the federated learning. That's what you were talking about.
He was talking about a different type of attack. Membership inference, he was talking.
If someone was in the database.
Yeah. Essentially, we have a layer of differential privacy, right? That I mean, we trust the data providers to use their own data and don't allow anyone to access it. And since they share intermediate results and we noise them up a bit, we are protected against that as well.
Yeah. No, it's not. So maybe we can talk offline. The typical attack that we are familiar with, that is to attack the intermediate results and to actually reverse engineer the data, and that's well protected here. So maybe you are talking about different type of attack, and we need to talk about. About SMPC and federated learning. Actually, the way SMPC would be a way of merging the weights. And there are several ways. There is also a fully homomorphic encryption. You can do SMPC, and you can do enclaves for this. And we selected the federated learning because it is sufficient for this particular, let's call it, security concerns of the parties involved. SMPC has its own specific issues with deployment. You need all the parties to be there at the same time when they exchange information. With this approach, you don't have this kind of requirement.
Thank you, Rina. I think we've got to...
We're about finished.
We're at time. Yes.
Yeah, okay. Thanks a lot for listening, and hope it was interesting.